All right, so how you guys doing today? Good, perfect. Thank you for asking. All right, so like I said, so please make sure you guys watch the video on YouTube regularly, so you can follow the on the direction of the lecture and pace. The last time we've been talking about the mass spec. We mainly talked about how you can use the mass spec to analyze your organic compounds. But we're actually going to deal with a little bit more different types of the organic compound with the functional groups. And at this time, we're going to use it for the analyzing the compound with the specific functional groups. So the last part that we talked on Monday was alcohol. So if you have alcohol, it's meaning whenever you have the compounds, you're going to have a hydroxyl group over there. Okay. So if that is the case, the one possible scenario you may see in the mass spec fragments is the what we call alpha cleavage. Alpha cleavage. Okay. So meaning they're going to break the bonds nearby as the functional group. So the carbon that is close to the functional groups, they're going to break the bond between carbons nearby as a functional group. So this is why this is sort of we can say alpha carbon here. But around that alpha carbon, we're going to have some breakage of the bond where you can find nearly near the functional groups. Okay. So if that happens here, when it's the like an electron bombard over here, you will see, oh, this might be the where you will see most of the time the breakage of the bonds when you have down to lots of different types of small fragments from the compounds when you do the mass spec over here. So whenever it happens, you're going to see this one will break apart. So we're going to give you some the radical structure over here. Okay. But and plus to this one, you're going to have this one, right? Okay. So you're going to means so this is this one, okay. And so one radical form and one with the charge. So it'll be carbon here and over here. Okay. You're gonna have this type of compounds over there. Okay. So if that is the oh sorry. Of course, it's a charge. If that is the case, they can actually go okay, should be good. They either go to the other structure, resonance structure over here, because if you think about this oxygen over here, okay, it has two lone pairs still over there. Okay, this is group 6 elements, but it has only two single bond from hydrogen and carbon over here. Okay, so this is actually why the carbon now it carries a positive charge. This only has 3 available around the carbon, but carbon is group 4. So now it makes sense once this electron bombard, the cation radicals become a radical, but this one will carry the positive charge. Okay, so if that is the case, you can also look at the resonance structure from this one, because you can actually use one of the lone pair to be donated in this bond, so you can make a double bonds. So that happens to this one. The carbon will be happier with the more electrons down there. So charge will be gone to oxygen, because oxygen now it only has one lone pair over there. Okay, so if you count the electrons over here, it will be 1, 2, 3, 4, 5 instead of 6. So now you have the charge is moving in this resonance structure back and forth. But overall, we can have those charged molecule after this alpha cleavage with the radical structure, which you see that on the bond breakage nearby as a function. Makes sense, right? We good? Okay. Can I move on? So by the way, I'll give you some example practical problem anyway. So this is some kind of like a brainstorm. Okay, so this is one scenario you can do with the alcohol, okay? So please keep this in your mind, okay? Okay, so the second scenario of this alcohol compounds, what you can possibly look at is the, obviously once again, you will have a hydroxyl group that makes this compound alcohol, okay? And then whenever it happens to the neighboring carbon with the hydrogen, what you can actually think of is the what? Dehydration, meaning they're actually going to lose some part of their compounds in the form of the water. This is H2O. Okay, so if that happens to this one, obviously this is also initially electron bumper, so very unstable. So that's why they make a small fragment, but in the form of a water first. So this is another possible scenario for the alcohol compound when it goes to the fragment and the mass. Okay, the water. So if that happens to this one, they're going to have a double bond in here. So, this one. So for alcohol compounds, this is also another possible scenario you can possibly see in the mass spec data. So only thing you really need to look at this one is the water. This water we know is 18 grams per mole AMU. So you may not see very clear molecular ion, which is your whole compound molecular weight, but that minus 18 maybe appear on the peak on your mass spec. You can see, oh, this might gone through the dehydration instead of other cleavage. So we'll actually take some time to look at it more in detail a little later, but this is another possible scenario, and I will tell you more about the other functional group as well, okay, real quick. But just keep this in your mind, okay, and then we're gonna get to the practical problems soon today, and I'll show you how to use this information soon, okay. But it makes sense though, right? It's dehydration, slightly different from the first one, okay. Okay, then okay, so the other one is the amines. Okay, so whenever you have amine groups instead of the maybe hydroxy group, you can have some also similar interactions too. So whenever it happens to the electron bombardment process in the mass spec, they will probably go through the similar reaction that you already saw for the alcohol. But this is the almost same, but this is only going to with the amine instead of alcohol. So if you look at this one in this way, you're going to the getting the positive charge. So this is very similar to the alcohol we just did in the first scenario. But just one thing, another thing is this is now, we know the nitrogen is a group 5 elements. So if you look at this one very closely, it only has 3 available valence electron around it right now. Means actually there's a 1 lone pair as well. So so you can always assume the lone pairs in hydrogen, sometimes implied in the skeleton structure, but we normally do. But we do know now, because only 3, there gotta be at least 1 lone pair on top of the nitrogen now. So you can also do, like you did for the alcohol, you can do the resonance structure. So you can do this one, but instead now the nitrogen will carry the positive charge. This is another possible scenario. Obviously, this is an example of alpha cleavage as well. Okay. So this is pretty much the same, but just with only difference is we have amine group instead of alcohol. So this is something you may also see if you have the compound with amine groups later on. Okay, so makes sense, right? It's pretty much the same. with the first scenario you saw for the alcohol. Okay, so let's move on to the one. So the other one is anything that has a carbonyl groups, or you can say carbonyl compounds. Okay, so meaning you have anything that looks like this one. Okay, so you have like a carbon with a double bond to the oxygen. You have R groups on the other side. Okay, so if that is the case, what can possibly happen is this one. So if you look at the nature of the single bond, you know they can always rotate, they can move around, right, among the axes. So what it does when it rotate, what they can do is they actually can do the sequential movement of the electron pair. They can do, and this one, okay? So as you know, this is possible, the motion of the electrons in a sequential way. So eventually, what they're gonna do is they're going to take this one, okay, over here. So they become when it goes to this one, this is where you're going to see the separation over here. Okay, so this is the. Do you see that actually? So this is actually implied hydrogen, but I just drew it because it's important here to make it happen. So when it goes on there, that will go to the double making bond over here. So that makes this part becoming this one, because this is where you break it. But this is picked up by this oxygen here. This is brought over here. But those two are coming into here. Okay. Kind of makes sense, right? Does it make sense? Does it make sense? We good? Okay. So if that is the case, you have this one too. Now there is this one. So double bond is gone. It's just over there. Okay. So you have this one over here. Okay. We can say this is a better way to put it. Okay. So this is what we call. This is kind of special because it's actually happened from the sequential motion of the electron when it's had the freedom of rotating the single bonds, and then it was found by scientists. So we call this McLafferty Rearrangement. Okay, that's the what we call. Does it make sense? Can I move on, or do I need to go over again? Does it make sense? You good? Okay. All right. So this is the one possible scenario you can have for the carbonyl compounds. Okay. Like an alcohol, it has another possible scenario you can do. So the carbonyl compound simply means you have the double bond to the oxygen here, meaning this carbon will have two different R groups. Like even previous one also had two different R groups, but because of the rotations, they could have actually specific McLafferty rearrangement. But also, obviously, like other functional group compounds, they can also go through the regular R part cleavage fragments as well. Okay? So maybe we can say the one is on here in the left, maybe just R group, but try to make this to distinguishable. Maybe we can add R prime over there. Okay? So maybe we can try to maybe click one of them. Okay? For example, so maybe you can put that in this position. Okay? Sorry, this is when it's very unstable. And then also you're gonna have this one over here. So when it's a break apart, this will goes to there. So you can have this one, okay? And then like you did before for the other compound, the functional groups, it has a 2 lone pair, as you know, because it's also group 6 element oxygen. So this one can also go to make a resonance structure. So now you're going to have triple bond between these two, and then you're going to have over here. So now once again, positive charge are shipped to the where you can find the oxygen. This is actually the one that you're going to do in one of the experiment in over 2. So you actually see this one sometime. Anyway, so this is also the second possible scenario for your carbonic groups over here. Okay? So make sure you guys put this in your mind, and then I'm gonna show you the practical problems you may see on the exam now. So I'll try to explain how those things will we apply to the actual problems on the exam quiz. Okay? So if that is all that, okay. So whenever you have some type of mass spec, the bar graph over here, once again, the x is the mass to the charge ratio, okay, which is simply same as your molecular weight of fragments. And this is once again relative abundance in a percentile units. So you can have a relative fragments quantity among the all the collected data. Okay. So if this is the case, maybe once again we can take a look of alcohol groups. Okay. You can try to get some alcohol groups over here. So if this is the case, this is alcohol because you have a hydrogen group on this compound. So this is a type of alcohol compound. And then what you need to do is, first of all, you need to find out what might be the molecular weight of the whole compounds first. Okay, so what we can do is try to do carbon, 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 carbon. Okay, and now we know there's a 3, 1, 3, 1, 2, 1, 2, and 3. Okay, right? So you can try to get the molecular weight of this one. Okay, so you can try to count the carbons. It's 1, 2, 3, 4, 5, 6. So that's 12, right? 12 times 6, 72. You can try to count the hydrogen here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14. Right? 14. Okay. And you have one oxygen over here. Because it's the 16. It's 16. Okay. So in total, you're going to get 2. 1 or 2, right? So you may see the maybe small peak of the molecular ion peak on here that we want to possibly, or very small, okay? Because like I said, those are the ones that will break quite easily, with especially the single bond with the hydrogen group. So you may see that, but the most importantly, you need to look at 2 possible scenarios. So once again, if it's the alcohol compounds, you may need to think about the alpha cleavage, right? And another possible scenario is a dehydration. So if you remember this one, we talked like 10 minutes ago, right? 10 minutes ago. Whenever you have a 1 or 2, if dehydration happens, you need to see the peak where? Minus 18, right? So meaning 1 or 2 minus 18 is 86, right? 109 minus 18 is 86. So after your molecular ion peak, if you see your another peak, major peak on 86, now you can say, oh, this has gone through dehydration for sure. And you know how those are fragmented on this fermented in this type. However, if you don't see the peak on 86, means you need to think about, oh, maybe dehydration has not happened to this compound, the fragment, but maybe alpha cleavage. Okay? So if that is the case, it's pretty much the same. Okay? If you have the alpha cleavage, this is the carbon that is close to the hydroxy group. So I said they're going to break the bonds near this carbon, mean either this one or this one, right? Because they're gonna not cut it easy from here and here yet, because this is where you can find the closest hydroxy group, right? So meaning you're supposed to see the daughter parts are either gone. So maybe you can lose this one or this one, either way, okay? So if that is true, this is once again, this is carbon 2, carbon 3, right? This is carbon 2 and carbon 3. So if you guys remember this, if this one break apart as a radical form, this is a 29. It's 2 carbon and 5 hydrogen. 12 times 2 is 24, plus 5 is 29, right? So if alpha cleavage happen instead of dehydration, you're supposed to see 1 or 2 minus 29 on the peak. Or this is when it breaks this part here instead, you're supposed to see this is now carbon, 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 right? But there's only one carbon because 1, 2, 3, 4, right? And there's 3 and 3 and there's 2 terminal carbons, right? So that makes 3 carbons is 12 times 3 is what? 36, right? But you have 7 hydrogen. Okay? So if you add them all, that's going to be 43. Okay? So either they're going to lose a 43 number or 29 will be on the peak if alpha cleavage really did happen. Okay? So if that is the case, you're going to see the peak on, so the 1 or 2 minus 29 will be 73, okay, 73. And if you have a 1 or 2 minus 43 will be 959, okay? So if you do see the peaks on those two, now you can say what? Oh, this had not gone to the dehydration, but it did with what? Alpha cleavage. Because I told you the 2 possible scenario you can have, right? Sorry. So if there is no number that is lower, this number minus 18, then it might not be the hydrogen, but it does show the 2 different numbers that correspond to the numbers you see from the outcome of the alpha cleavage. Then you can say, oh, this is for sure alpha cleavage. So in your exam, if I show you this, the mass spec graph, maybe you can tell me if it's gone to dehydration or upper cleavage by looking at those numbers. That's it. Make sense, right? Good, perfect. Okay. So you don't know more than that, because I know you don't have to draw the structure, analyze the bar. That would be too much for the 1 hour exam. So only thing you really need to know is just the work. You just need to get the molecular molecular ion number and do a bit of a subtraction and possible fragment you may see from the either upper cleavage or dehydration. You can look at that numbers to the one of the multiple choice and you can say the right answer. Okay? Or you can choose either upper cleavage or dehydration in other options as well. Vice versa. Does it make sense? Good? Oh, perfect. All right, so let's do just one more. Okay, just one more. And then maybe we can move on. Okay. So if that is the case, once again, beside alcohol, we have also carbonyl groups that may have some type of. So if you have some carbonyl compound, it also may have some other, But from here, what you can also predict from here is you can try to think about the upper cleavage. They might be too small to be McLafferty rearrangement, so you can think about the upper cleavage over here. But the point is, they're either going to break near the alpha carbon here, so they're going to break this one and this one. So meaning they're going to have the fragments of this one will be removed, and the other part will be detected on the detector on the mass spec. So you can possibly have this vertical structure with this one. This one. But anyway, I did not show you the lone pair because it's implied there. But if that is the case, you may see is that once again, we're gonna do pretty much the same thing what we did. Okay. So first of all, you just need to know what's the total molecular weight first. Okay. So once again, it has a carbon, 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 right? But this is terminal carbon, so we know there is a 3 hydrogen, right? So there'll be 3 hydrogen here. There'll be 1, 2, 3, 4. So there'll be no hydrogen in this carbon. There'll be 1, 2, 3, and 4. So there'll be 2 hydrogen here, and this is a 3 again. Okay. So now we have a carbon, hydrogen, and oxygen. So we can try to do the molecular weight calculations. It'll be 4 times 12 is carbon is 48, right? And you have 1 oxygen, so it'll be just 1 oxygen. And then you have a 3, 4, 5, 8, right? So it'll be 8 hydrogen over here. So if you just sum it all, it's 8, right? Yeah, I think so. So if you do that, there will be 2, 72. Yeah, 72. Okay. So now you got what you just found out was your parent peak, molecular ion peak, right? And then let's say if they really did book those 2 over here, you could see once again, this is going to be 29 that you're losing because it's carbon, carbon, 5 hydrogen. If you're losing here, it will be 15 because it's 3 hydrogen, 1 carbon. 12 plus 3 is 15. So you have some over there. You're not going to have a lot of this one lost because this is kind of hard to break. So, but you so okay, 72 minus 15 will be 57. So you have some 57, but you have a lot of 29 minus thing. So it'll be 72 minus 29 will be 43. So if you do see those the mass spec, you can be for sure that is indeed the upper cleaves that happen to your two butanoids, or you can say methyl at the ketone, doesn't matter. But the so this is kind of a way to apply your knowledge to analyze your compound on your mass spec graph. It indeed actually tell you and the specific number, so you can tell, oh, this is indeed the upper cleaves, and it was indeed for that correct compounds as well, with a certain functional groups. This is really good because you can actually tell that with a specific number. This is what we call this mass spec spectroscopy. Because metry simply means you have a quantifiable data you can collect from this the analysis. Okay. Does it make sense? Are we good? Oh, perfect. All right, so that's really good then. This is pretty much all that I want to know for the exam, which you have a little bit of a practice maybe, but if you do have any other questions, just let me know. Okay? And then we can go over mass spec again in my office, but I think you guys did really well so far, so that's great. So the later part of the chapter 12 is about the IR spectroscopy. So IR simply means it's infrared, the spectrum. Meaning, the IR is just the one type of the light, because you can see the light is have a very long range of the spectrums. You can see the visible light, or you can do ultraviolet, gamma ray, microwave, so forth. It depends on where you can find this light in the long spectrum. And one of it is infrared, the light. So this is just the light, this one part of the light spectrum you can locate. Okay. So before I get to the IR spectroscopy, there's a couple of things that I need to tell you is whenever you look at the light, this is a quick review from the Zenken 1 and 2. You have this type of equation many times, because this is the speed of light. Speed of light in vacuum is about 3.0 times 10 to negative 8 meter per second. This lambda means this is a wavelength. Okay? This is a wavelength. Normally we put it in meter because we have a unit for the speed is meter per second. So we normally do the meter, but as you know, the wavelength of the light is very short. So for our convenience, we actually use nanometer, which is 10 to negative meters of our meter, 1 meter. So, and then this is the frequency, as you know, it's a frequency. It just simply tells you how many of something happened per period of time. Usually we use per second. Once again, it's because of the unit of the speed of light. So you have the meter per second. So this is why I put the numbers in the wavelengths in meter. We want to find out how many things happen per 1 second because of this one. So simply what it really tells you is if you look at the light, as you know, the light is simply electromagnetic radiations. They're going to have an oscillation of the magnetic field and electrical field. So this means they're going to have types of the wave generated as they travel through the space. Okay. So if they do this and do that, or do perpendicularly, but whenever they do have a wave property of the light, we learn about this duality of the light with the matter, but one of them is obviously the wave. So if that is come to the here to the here makes one wave, that is the length of the one wave. So we call that wavelength. But think about the frequency is how many of something per second. You can actually tell how many waves will be generated over 1 second. So that is why if you multiply these two, that makes speed of light. So you now know if I step twice per second, you can measure a length of my 1 step. If my length of 1 step is 0.5 meter, if I can step twice per 1 second, that means 2 steps 1.5 times 2 would be 1 meter per second. So it's the same thing goes with the light. If you know the wavelengths and how many waves, you actually tell how fast it can travel. Makes sense, right? Yeah, perfect. So if that is the case, there's another thing you need to know from here is the energy of the photon, quanta, or electrons are coming from the quantum, meaning the smallest of something. That comes with the Planck constant, okay, Planck constant times the frequency. So the key point here is that this is something that some scientists really didn't like, because it actually means the concept of a quantized energy. Do you guys remember this? Quantized, the quantum mechanics is very briefly in the Jenkin 1 and 2. Especially meaning the energy of the light is not continuous. So they're not going to be 0.5 photon energy. They're only going to be 1 photon energy, then 2 second photon energy, but they're not going to be 1.1 photon energy. Meaning all the energy levels from the light or heat is all quantized. So there's nothing between in the steps. So quantized energy means you're going to have energy increased by like a stair. So they can go up here and here and here, but we don't see the energy increase by like gradually. This is not possible. This is why each levels are certain numbers there, certain level. So that's why we call this quantized, because it's quantity is fixed. There's no between. So there's no energy in here and here and here, only certain levels. But we didn't see this one until the very modern physicist era, because those gaps are very small. So if you make a very small stairs and small, it just looks like a gradual increase. But we indeed find out, we find the electrons, we find some of the photons, we had quantums of light, quantums of matter. We now start looking, it's just very small, but it's not gradual, it's quantized. So the reason why I'm saying this so importantly is this is a basic mechanism to how we do the IR. Because the IR is simply, we try to analyze how much of the each energy, each quantized light absorbed to the compounds. Because of this, the molecules also have a specific motion with their bonds. Like either they do the symmetric, asymmetric, or they do the plane bending, or outflow bending, or twisting, and there are all types of the motion. But it only happens at the specific frequency of the vibrations because of the quantized energy. Meaning, if you have a certain wavelengths that kind of oscillate in the same frequency of that light, they're gonna absorb the energy. So certain compounds or certain functional groups will only observe a lot of that portion, that energy light in the range of the IR, infrared, the light, not the visible or ultra or gamma, because they're too strong to be observed to the compound. So there's a certain range of the spectrum. You can use it for the analyzing that way. Is IR. I'll do it again on Friday, but I'll stop here. But does it make sense?